Okay, so any questions about web work?
Can you talk about number 7?
Sure. Let me get this screen up and running here. Easier said than done, apparently. So I guess the computer's thinking deeply about something right now. Whatever it is computers think about. Working on it. Wow, it really is in deep thought. There we go. All right. So web work and 7, did you say?
Yeah.
Which is not this one. Let's go here and here. All right. So we've got this temperature function. All of them, or any particular parts?
C and D especially.
C and D. Okay. So level curves were probably on the lines of circles or something like that. At what point on the plane is it hottest? Probably near the origin. Okay, so C. Find the direction of greatest increase in temperature at the point 1, 3. So the direction of greatest increase of any function is always the direction of the gradient at that point. So you take the gradient of this function, which is not terrible, but it's going to take a little bit of work. So you can do the gradient. Okay, you take the gradient, you plug in 1, 3, and that's going to give you the direction of maximum increase. And then what's the magnitude of that greatest increase is really just what's the magnitude of that vector that you just plugged in previously. Okay? This problem does have a bit of a typo in it, in my opinion. In part D, it says, what's the direction of greatest decrease? Well, if the gradient points in the direction of greatest increase, how do you turn that into the direction of greatest decrease? Just turn it around, which means multiply the vector by a -1, which means multiply each component by a -1, and that's the direction of greatest decrease. And then it goes on and it says, what's the magnitude of greatest decrease? In my opinion, that's a positive number, which is the magnitude of the vector that you just calculated. And in fact, it'll be the same as this answer. They, for some reason, wanted a minus sign there. So if you get this value, this value right here, and put it in here with a minus sign, I think that's the right answer. That's what web work wants. What I would want is the positive number. Okay. So the difference is, if you want a minus sign there, what you should have asked is what's the directional derivative in that direction. The directional derivative has sign to it, has a plus and minus value to it, but magnitude never has is never negative. Other questions? Lila?
Can you do number 2?
I'll try. Okay, so okay. So number 2, we are given the surface, and there are 2 points, A and B, that are of interest, and you're asked to go through and find the sign, SIGN, of each of these quantities. I'm guessing that you can do all the first partials? Yeah, everybody? Okay, and what you're probably interested in are the second partials. The second partials here, for example, you have f sub xx. Do you remember what the second derivative meant in Calc 1? Geometrically, concavity, right? Geometrically. I mean, it means all of those things that you just said, but in the context of a surface like this, it's geometrically it means concavity. And so, for example, in Calc 1, you learned that if the second derivative was positive, then it was concave up, and if it was negative, then it was concave down. And that would tell you something about whether it was a maximum or a minimum. So you could use the second derivative test. That exact same intuition carries over here. So let's look at fxx at b. All right, so here's the x-axis. So what we're talking about is the second derivative in the x direction, which means we're talking about the concavity through b in the x direction. So let's look at it from the side there. And what is the concavity in that direction? It's down, so it's negative. And so you call that negative, and you can just go through in the y direction. And that's why they don't really ask you about xy, because it's really hard to put any kind of, to see any kind of geometric significance to the mixed partial. But the straight up second partials, fxx, fyy, those do have geometric significance. And they talk about and they show you about concavity. Okay. Any other questions? Did everybody get, I think it was this one. Everybody okay with these? Okay. Ask me that question again.
Are we actually supposed to try to figure out the sound
No. Okay, so now you're interested not in the derivative in the x or in the y direction, but in this direction, or this direction. And so what you have to do, I think probably to start out with, the easiest thing to do is to look down from above. And here the x-axis is oriented, this is the positive end. And here, the y-axis, this is the positive end, and this is the positive end of the x-axis. So it's the usual way that we look at these things. And then we go to the point 2,1, which is conveniently marked in red. And we get to that point, and we look in the direction 2I plus j. So here I am standing at this point. I want to look in the direction 2I plus j, which is somewhere along that direction. Does everybody see that? So if I stand here and I look in that direction, what's the surface going to do? Fall or rise? It's going to fall. And if you don't remember, let me pull it up. Right? It's going to fall. And that tells me that that directional derivative must be negative. Okay. I took a little bit of issue with this problem. But I hope that at least it makes sense, even if WebWork was a little bit picky about some of the answers. Some people were getting 0, or WebWork was asking for 0 in a place where I wouldn't have asked for a 0. There are situations, for example, if WebWork sent you to this point and asked you what the directional derivative, what the derivative was in the, say, I direction, that I'd call 0. So if you're sitting right here and you look in this direction, I'd call that 0. Because you're right sort of at that boundary there. But anyway, I don't want to get too fussy about it. You guys understand the concept, right? You put yourself on the point, you look in the direction, and you figure out whether the surface is falling or rising. And my exercises will be, or any questions that I ask you on an exam, for example, will be very clear about what that is. This was somewhat ambiguous in certain instances. Okay, so let's talk about the topic of the day. Topic of the day. Let's switch over to notebook mode. All right, So what we're doing now is finding extrema of functions of two variables. And by extrema, I mean places local maxes and local mins. And extrema is a good word because it sort of captures all of that in one fell swoop. Let me remind you, let me pull up a picture here. You'll remember this Java application that plotted surfaces. And I think just the default function is enough for me to illustrate my point. Okay, so this default function is just a paraboloid, x squared plus y squared, right here. And if you'll remember, and I know it's hard to see, but if you remember, one of the nice things about this application is it shows you the traces, or the traces in the x and the y direction. For example, the yellow curve is the trace in parallel to the x-axis, and the blue curve is the trace parallel to the y-axis. And what do you notice about these guys, or what you do notice about these guys, is that each of these curves independently has a place where it has a minimum. And if you were to take the partial of the yellow curve with respect to x and set it equal to 0, you would get that point showing up as a possible minimum point, or as a possible extreme value. And if you did the same thing in the y direction, you would get, again, another point in the y direction. But you notice that the surface itself does not have a minimum at either one of those places. To get the minimum of the surface, you have to get those two minimums to coincide. And you can actually do that if you slide this guy right. If you slide those guys down to where they both have a minimum at the same place, then that's also going to be a minimum of the surface. And that's essentially the main takeaway for today. How do you think you find those places where those minimums coincide? Algebraically, what do you think you have to do? Set what? Set the first partials equal to 0, and what you're going to get is two equations and two unknowns. If you can find solutions to that system of equations, those are candidates for extrema, local extrema. They may not be local extrema, but if you're going to have one, it's got to happen that condition has to be met. And that's kind of where we're going to go. That is where we're going to go today. So let me close that, and let's go back over here. So we can find candidates by doing that. And I use the word candidate because just like in Calc 1, there are going to be places where both of these partial derivatives are 0, and yet the point is not a local extrema. It's neither a maximum nor a minimum. Do you remember in Calc 1, right, where you had this function that would go like this and it would level off, but then it would keep going up? Right? That point where it levels off, the derivative is 0 there. But that point it's neither a maximum nor a minimum. And that still happens in Calc 3. And in fact, it gets even more interesting because not only do you have that place, that's odd situation where the derivative is 0, but you all, and it fails to be an extrema. But you have other more interesting situations that I'll illustrate today. Something called a saddle point, for example. All right. Or I'll do an example today where the surface has 2 local maximums and no local minimums. That should be weird to you. So I'll show you an example today where we have 2 local maxes, right? Here's a maximum, here's a maximum, and there's no local minimum. So how do I get from here to here? All right, here's a max, here's a max. How do I get from here to here without having some kind of minimum? All right, I will show you that today. All right. So, some things in Calc 3 are more complicated than Calc 1. Some things are easier. Here's one that's more complicated: the second derivative test. Okay. Here was essentially a summary of the second derivative test for Calc 1. If the second derivative was positive, then it was a minimum, right? Because it's down here at the bottom. And if the second derivative was negative, then it was a maximum because it's up here at the top of this hill. Okay. Hold on to your hats here. I'm not going to prove this theorem. In fact, I don't know of any Calc 3 book that proves this theorem. It's more of an advanced math course. I'm teaching a class right now called Differential Geometry, and I might prove this result that I'm about to show you. I might prove it sometime in November. It's a 400 level class. Okay, so it's definitely out there. The second derivative test relies on more than just the second derivatives. It relies on this exotic expression called the discriminant. So we're going to let the discriminant of f be defined as capital D. It's the second partial of f with respect to x times the second partial of f with respect to y times the mixed partial of f squared. So we're going to define the discriminant of f to be this quantity, and then we have this theorem. 1. If the discriminant is greater than 0 and f sub xx is less than 0, then and let's let x naught y naught be a candidate. What do I mean by candidate? The first partials are 0. So this is a place where the first partials are both 0 at the same time. So if D is greater than 0 and fxx is less than 0, then the candidate is a local max. Okay, 2. If D is greater than 0, again, still greater than 0, and fxx is greater than 0 as well, then x naught, y naught is a local max, a local min, sorry. Third condition, or third possibility. If D is less than 0, then no matter what, then if the discriminant is less than 0, then this point is neither a max nor a min, and some call this a saddle point. And I'll explain why later. And finally, there's one condition left, and that's if D is equal to 0, then there's no information. You have to resort to some other means to classify the candidate. The discriminant doesn't provide any information. So that candidate could be a max, it could be a min, it could be neither. And you have to go somewhere else to figure that out. This seems like a lot of conditions, a lot of branches in the decision tree. Let me try to reassure you a little bit. Let me try to parse some of these things for you. If the discriminant is positive, then there's a decision, right? Then we know something. We know that it's a maximum or a minimum. So that's right off the bat. Now, how do we decide? Well, luckily now we can fall back to good old Calc 1. Because this is really just the concavity. And what we're saying is, okay, the discriminant is positive, so it must be one or the other, a max or a min. Let's look at the concavity. Here, this is concave down, right? So it must be a local max. This is concave up, so it must be a local min. So if D is bigger than 0, then essentially you're back in Calc 1 land. All right. If D is less than 0, then it's a saddle point. It's neither a max nor a min. There are places around this point that are higher and places around the point that are lower. And you're done. Not a max nor a min. And if it's equal to 0, then there's no information. You go somewhere else. You might ask yourself, why are we picking on fxx? Given that there's a perfectly good fyy over there, or fxy, for example. Well, and the short answer is no reason. I could put fyy here and get the same theorem. Okay. What's going on here? Just again, really briefly, I don't want to dwell on this thing. Mostly, I want to just focus on execution. How do we use this thing? But remember, fxx is concavity in the x direction, and fyy is concavity in the y direction. If this thing is positive, what it means is those concavities agree. And so it doesn't matter which one we look at. And I'm getting perilously close to the proof, but that's what's going on. This thing tells us that the concavities agree when it's positive. When it's negative, what it means is the concavities disagree. And that's a saddle point. It's a maximum in this direction, but it's a minimum in this direction, and therefore it's neither. So when the discriminant is negative, it says that these concavities disagree. And then finally, when the discriminant is 0, we have no information. So hopefully that sheds a little bit of light on why this thing is the way it is, even if I haven't proven anything. Questions about that? All right, let's apply this thing. I'm going to apply this this process in, I guess, in increasingly applied ways. So I'm going to start out with a very dry, very straight up mathematical problem. Then I'm going to sort of move up to sort of a mathy yet geometric kind of problem. And then I'm going to finish with just a straight up word problem. Yes, there are some word problems in this section. All right. So here's a straight up dry mathematical example. Let's look at the following function. And let's find and classify the extreme values. All right. Well, let me just tell you how this is going to go. We're going to set the first derivative is equal to 0. We're going to find candidates, and then we're going to take those candidates and try the discriminant theorem with those candidates on each of them. So in order to do all of that, we're going to need all the first partials and all the second partials. So probably a good way to go at this point would just be to find all of those guys. So I'm going to go through and compute all of the partial derivatives up to order 2. So the partial with respect to x is 4y minus 4x cubed. The partial with respect to y is 4x minus 4y cubed. The second partial with respect to x is going to be minus 12x squared. The second partial with respect to y, minus 12y squared. And finally, the mixed, the mixed guy is, say, the derivative of x with respect to y, which is just a nice 4. All right, so let's find candidates first. So we're going to let f of x equal to 0, f of y equals 0. fx is 4y minus 4x cubed. fy is 4x minus 4y cubed. 2 equations, 2 unknowns. Now you got to pull out all the algebra that you know to solve equations like this. Sometimes they're pretty easy, sometimes they're impossible. I will try to give you easy to mediocre, easy to medium kinds of problems. Sometimes these problems are so hard that you can't actually even solve the equations. You just have to use a numerical approximation. I have to say that the business of minimizing and maximizing functions is a really large area of mathematics. What we're doing right now in this class, and all we're going to do in this class, is look at a very narrow band of problems where we have functions of 2 variables and we're trying to maximize or minimize. We're trying to optimize. Well, one might naturally wonder, can I maximize or minimize a function of 3 variables? The answer is yes, but we won't do that in here. And in fact, there are mathematicians and physicists and economists out there that are maximizing and minimizing functions of hundreds of variables, which is a really hard problem. And it pulls in all kinds of rich mathematics. You look at the gradient of these functions of hundreds of variables, so the gradient vector has hundreds of entries in it. You set the gradient equal to 0, which means now you have 100 equations and 100 variables and you're trying to solve these things. It really gets messy. 99.99% of these jobs are done on computers that are running massively parallel operations to find solutions or approximations of the solutions. Why do we care so much about maximums and minimums? There's a lot of information to be had there. If you want to, right? For example, if you're someone in risk management and you're selling insurance, right? You want to maximize your profit. Well, you've got to sort of balance the demand for your insurance versus the risk in pricing these things. So when you're pricing things, you're often solving max-min problems. Or let's talk about airline tickets, right? You got whole rooms of people with computers pricing airline tickets. And these tickets, I don't know if you've bought tickets recently, but the prices on these things change moment to moment, almost. Right? You log in 1 minute and you got $250 to get down to San Diego, and then you log in 3 hours later and you can't find anything under 400, right? And that's because these nitwits are in these rooms back there running these algorithms trying to maximize profit, right? Based on what they think demand is going to be for that particular weekend, yada, yada, yada. And there are hundreds of variables involved, and they're cranking and grinding. But at the foundation are essentially processes like this: setting first derivatives equal to 0, testing those things to see if they're extreme points. So this is a very baby version of a much larger world called optimization, and it's a huge industry. I mean, if you want to get a job in the mathematical sciences, go into optimization. It's a huge industry. All right, all these big companies, Walmart and so forth, they all have optimizers, people that work in these rooms and build these formulas and models and optimize. That's all they do. Okay, so let's solve this equation. How do you think we solve this equation? 2 equations, 2 unknowns. Ideas? We could set them equal to each other. I think I'm a bigger fan of solving for one variable and substituting in to the other. So let's do that and see what we get. If we use the second equation, we see that x is equal to y cubed, right? So I'm going to take that and dump it into the first equation. So if x is equal to y cubed, then we get 4y minus 4, 4y to the 9th equals 0? Yeah? Okay, it's not so bad. What's that? Y times 1 minus y to the 8th. I said 8th equals 0. Solutions of that equation. Certainly y equals 0 and 1 and negative 1. It's probably the first time you've ever solved an 8th order polynomial. If you take complex analysis, you can find the other 6 solutions of this equation. Yes, there are actually 9 solutions of that equation. 6 of them are in the complex plane. So if you're interested in that kind of thing, take complex analysis. I'll teach it next year. Okay. But we're only interested in real solutions. And so we've got 0, 1, and negative 1. So 0, 1, and negative 1 correspond to what x values? Hint, hint. 0, 1, and negative 1. Okay. So we've got 3 candidates. 0, 0, 1, 1, negative 1, negative 1. Yeah? They're candidates because we don't know what they are at the moment. So where are we going to go now? We're going to do the second derivative test. We're going to compute d. So let me write out d in all of its glory first. So d is fxx times fyy minus fxy squared. And let me clean that up a little bit. That's 144x squared y squared minus 16. And we want to run the test on these 3 points. So let's do the test on 0, 0. What's d of 0, 0? Negative 16, which is less than 0, right? So how can we classify 0, 0? It's neither, right? It's a saddle point. Okay, let's do 1, 1. What's d of 1, 1? Well, I don't know what it is, but what do we know about it? It's positive. And you don't have to compute the value if you don't want to. It's positive. So if it's positive, now what do we do? We have to look at fxx now, right? Okay, what's fxx of 1, 1? Is it still on my screen? No, it's not. fxx of 1, 1 is negative 12. Again, don't really care. It's negative. Okay, so what's that mean? Good. Okay. Last one. What's d of negative 1, negative 1? Don't really know, but it's positive. What's fxx of negative 1, negative 1? Don't really know, but it's negative. This is local max. This is that surface that I was telling you about. 2 maximums, a minimum, and nothing else. How can a surface have 2 maximums and not have a minimum in between?
What should be minimum is the side.
Exactly. You want to see what it looks like? All right. Yes, I want to see what it looks like. Wow, this computer is so persnickety today. Hold on for a second. I'm starting Maple and trying to switch over at the same time, which is probably not a good idea. There we go. Okay. And let's blow this up a little bit. All right, so I'm going to plot this surface, and I'm going to plot those 3 points as well. So let's let the surface be, gosh, if I only had a mind. Oh, I have it written down right here. Good. Let's see, the minimums, the points are all like 0, 0, 1, 1, -1, so I'm going to go -2 to 2 just to get everything in there in both directions. Okay, so there's the surface. Let me get the first point. 0, 0, 0. And let's make it red. And make it large. All right. Not what I wanted. Enter. There we go. Okay, the second point was 1, 1. What's the z coordinate for 1, 1? Two. Good. We'll keep it red. We'll keep it big. The third one was -1, -1. What's the z coordinate for that? Also 2. Good. Okay, I want to put all of these guys on the same axis. Oops. Didn't want that L in there. There we go. Alright, and let me turn on the... Okay, here we go. Those are them. Okay, and if you look really closely at that middle point, that's what somebody, I don't know, was it Ryan or somebody said, or Andy, this is a saddle point. So it does go down to a minimum in this direction, right? But if you look at it in this direction, it happens to be the top of a little hump, which is really hard to see, but it happens to be the top of a hump that goes in this direction. So that point right there, the saddle point, is neither a max nor a min, but it serves the role, or it plays the role of that intuitive minimum that you expect to be there between the two maximums, right? So to get from this max to this max, I went down and back up, and there was a min there, but it was only a min in this direction, right? In the other direction, there was a little bit of rise. Sorry, a little bit of fall in both directions. Does everybody see that? So your intuition can fail you at least early on in this subject, and that's a classic example of where it can fail you. Right? You think, oh, a max here, a max here. There must be a minimum in between. Not quite.
What would the discriminant come out as if instead of it having like a negative, like being a maximum and a minimum, it was a maximum and then just nothing? Like it was just flat, or
Like a plane?
yeah, or if it's flat in the x direction at that point.
So if
Instead
it's
of being
flat in the x
rectangle.
direction, if it's flat in the x direction, you still have a 0 first derivative.
Okay.
And then what's going on in the other direction can still play a role. But
would it be a minimum?
let's talk a little bit about this discriminant equals 0 case. The discriminant equals 0, and I think this is what Ethan's getting at, is what that really is telling you is that that's a very flat space. That's a very flat area of the surface. When the discriminant is 0, it's very flat. What does that mean by very flat? I'm not going to get into that, but it's flatter than the way it is at the top of this hump. An example of this in Calc 1 is y equals x to the 4th. When you get down to 0, that function is very flat down there. And in fact, the first derivative is 0 there, the second derivative is 0 there, the third derivative is 0 there, and you have to go all the way down to the 4th derivative to get a non-zero value at that point. And derivatives, in a sense, 0 derivatives, the more 0 derivatives you have, the flatter that area is. So if you have first derivatives equal to 0, you've got some flatness, but it's max-min territory. If you have all the second derivatives equal to 0, then you've got a really flat surface. You've got a 0 discriminant, and you have to bring in other equipment to classify these points. Okay, really flat surfaces are harder to analyze in a sense, or maybe in some ways they're easier to analyze because they're just flat. They're like planes. All right, let's do another. Oh yeah, we've got plenty of time. Any questions about this guy? All right, let's do another one. I'm gonna leave this open. I might come back to it. All right. Now what I'm interested in is let's do a web work problem. There's one somewhat interesting web work problem. Which one is it? It's number 7. No, it isn't either. It's number 4. Okay. Here's a web work problem for you guys. So you'll be doing this one in the next 48 hours, although I'm going to do most of it for you right now. We've talked a little bit about this before. The people that created web work, one of the hard problems that they have to deal with is the wide variety of answers that students can come up with, correct answers, right? So you can have lots of different ways of expressing the same correct answer. And so as a programmer, when you write this web page, you have to take that answer from the student and try to do something to it to figure out whether it's the right answer, right? You can't just sort of have the right answer in there and match it. And if it matches, it's correct. And if it doesn't match, it's incorrect, right? Because you can express the same answer in lots of different ways. So the second sentence here is what I want to first focus on. They're asking you, you're going to get 2 answers to this problem. And in order to sort of make the job of the programmer a little bit easier, they're going to try to get you to put one of those answers in the first slot and the other answer in the second slot. And the way they're going to do this is by defining this thing called lexicographic order. And I just thought it was an interesting aside, so I'll talk a little bit about it. You can order points lexigraphically, points x, y, and z lexigraphically, in the following way. 1 comes before 2, comes before 3. So it's sort of like alphabetical. A comes before B, comes before C. But in the case where the x-coordinates are equal, there's a tie in the x-coordinate, then you have to go to the y-coordinates. And then you do the y-coordinates lexigraphically. 1 comes before 2, comes before 3. And in the case where x and y agree, you have to go to the z-coordinates to break the tie. So what they're talking about here, let me do a quick example in the notes. Let's pretend that I have a point A and it's, say, 1, 10, 0. And then I have another point B and it's, say, 1, negative 10, 0. Which comes first in lexicographic order? B. Okay, so there's a tie in the x-coordinate. And so now we go to the y-coordinate. And whichever y-coordinate is smaller, negative 10, wins. And then if there were a tie there, you go on to the third coordinate. So that's how they want you to enter the data. All right, let's look at the actual problem now that we understand how to enter the data. Find the points on the surface z squared equals xy plus 1, which are closest to the point z11, 0. So when you see a word like closest, what you're being asked to do is minimize something. And in this case, you're being asked to minimize distance. So what we want to first do is come up with a quantification of distance, the distance to 7, 11, 0. That's the thing that we want to minimize, right? So we want to minimize the distance to 7, 11, 0. Well, if I'm a point, x, y, z, for example, how far am I from 7, 11, 10? How do I figure that out? Distance formula, right. So I'm going to call that capital D, even though I've used capital D in other places. I'm going to call that capital D. And that would be something like x minus 7 squared plus y minus 11 squared plus z squared, all square root. Okay, and here's the first word of wisdom that I'm going to give you, and this is something that will be useful in physics and in other math classes. Whenever you minimize distance, it suffices to minimize distance squared. So, in fact, we'll consider instead, the function d, which is x minus 7 squared plus y minus 11 squared plus z squared. Now, why is it preferable for me to minimize little d versus big D? Sorry? How? Where is that going to be a problem? Or maybe not a problem, but an annoyance. When I compute those partials, right? The first partials, they're going to be bad. The second partials are going to be even worse. So, word to the wise, whenever you're minimizing a distance function, which you'll do probably a few times in the next couple of days, minimize distance squared. Get rid of that radical. All right. Now, if I were to minimize this function just as it is right now, what's the answer? 7, 11, 0, right? How do you minimize the distance to 7, 11, 0? You just be 7, 11, 0 and you're done. Why is that not the answer to this problem? What's the problem with 7, 11, 0?
It's not on the surface.
It's not on the surface, right? So the surface, we haven't really figured out how to get the surface in there yet. Let's do that. So we know that we want to minimize this distance function. Now, a strong hint that you're not ready to minimize yet is the presence of 3 variables. Okay? In this class, in this section, we're only minimizing functions of two variables. So there's too many variables, for lack of a more technical reason. How do I get rid of one of those variables? I introduce the constraint. I impose the condition that the point xyz must be on the surface, z squared equals xy plus 1. What does it mean for a point to be on that surface? If I give you a point, 3, 3, 9, how do I know whether it's on the surface or not?
X times y plus 1.
Right.
equals-
Does it satisfy the equation? Right. Does 3 times 3 plus 1 equal 81? No. So, fail. Okay. So, what am I going to do with this fact? I'm trying to minimize D. D has too many variables, and I have this extra constraint.
If you have a z squared and a distance from there, you could just plug that in.
So I could express this third variable z in terms of x and y, right? And sort of kill two birds with one stone. Now I've got a function of two variables which I can minimize or maximize, and I've introduced this extra information that it has to be on the surface. So let's do that. And I have to warn you, it's not always this nice. It's not always the case that you have a z squared sitting here and conveniently z squared is equal to xy plus 1. Sometimes you have to do a little bit of algebra, maybe solve for one of the variables, that sort of thing. But in this case, it just works out nicely. Now I'm ready. I've got a function of two variables. Let's go through this. So what we should be able to do now is differentiate this, find the first derivatives. We'll do the second derivatives too, but let's do the first derivatives. D sub x is 2 times x minus 7 plus y. D sub y is 2 times y minus 11 plus x. And d sub xx is going to be 2. D sub yy is also going to be 2. And d sub xy is going to be 1. Well, so the discriminant's pretty easy here. It's a constant. Dxx times dyyy minus dxy squared. That's going to be 3. We'll use that later. Okay, so we want to first find the candidates. How do we do that? Set first derivative is equal to 0. I'm going to do a little bit of algebra in my head here, which is always dangerous. 2x plus y equals 14, and x plus 2y equals 22. Does everybody see where those came from?
No.
I set the first derivatives equal to 0 here and here. And then I've got 2x plus y, and then there's a minus 14, which I moved over to the right-hand side. Now is everybody good? Okay, excellent. This is two equations, two unknowns. These are linear equations, so this is pretty straightforward to solve. Again, I guess I'd recommend just going with solve for one variable substituted into the other. So let's solve for x here. So x is equal to 22 minus 2y, and take that and drop it into the first equation. So now we get 44 minus 4y plus y equals 14. And That's 30 equals 3y, or y equals 10. I don't know. Okay. It's good to keep me on my toes, though. Okay. X, what's x? If y is 10, what's x? 2. So you take that guy, plug it in there, and you get x is equal to 2. So I said find candidates, but there's really just one. And that guy is 210. Now, is this a maximum or a minimum? This is a minimum, right? This is a distance problem. It's a minimum. But let's verify that it's a minimum. How are we going to do that?
Check that D is positive.
So D is positive, right? Because it's always 3. And now what do we need to do? So we know that D is positive. So now we need to look at fxx, or dxx, excuse me. dxx is 2. That's positive. So what does that mean? Local min. So don't forget to answer the question. The question is, which points on the surface minimize the distance to 7, 11, 0? What we found are the x and the y coordinates of the point on the surface that minimize that distance. To answer the question, you now have to go find the z coordinate. So we know that z squared is equal to x times y plus 1. X times y is 20, 21. So z is actually plus or minus root 21. So you get two answers. 2, 10, root 21, and 2, 10, negative root 21. Now you go back to web work and you punch these in. Which one goes first? The negative one, the negative root 21.
Weren't there 3 slots for answers?
There are 3, and they're just trying to be tricky. They don't want to give away too much. Right, so if you look at this, it says, leave unneeded spaces blank. Yes. Again, you wouldn't want to give away too much. All right. Any questions about that? No? Okay. One last problem. This is yet another of these sort of toy minimization problems that look really familiar to Calc 1 students. The big difference is we now can deal with one more degree of freedom, I suppose? Yes. So now we can deal with minimizing functions of 2 variables instead of minimizing functions of 1 variable. So let me finish up the period with this example. So let's determine determine the dimensions of a rectangular box open at the top with volume 32 cubic feet requiring the least amount of material. Pretty straightforward, classic max-min problem. The big difference here is we can now deal with 2 degrees of freedom instead of just 1 degree of freedom. So let me sketch a picture for you. sides. There's the box. Get some names on some of these sides. So the box is completely defined by the lengths of its three the three dimensions, length, width, and height. What's the volume of this box? X, Y, Z, and we know that it's supposed to be 32, right? And if you want to minimize the material, what's a proxy for minimizing material?
Surface area size.
We want to minimize surface area. So let's compute the surface area of this guy in terms of X, Y, and Z. What's the area of the bottom? X, Y. And there's only one face of that size because the top is missing. What's the area of the right side? YZ, but there are two faces like that? And then front and back? So there are two front and back equal XZ. Got it? Okay. What is the quantity that we're trying to optimize? S. That's the thing we're trying to optimize, in this case minimize, right? Too many variables in S, right? So what do? Eliminate one of the variables using the volume constraint. Which one do you want to eliminate? Z. Everybody wants to eliminate Z. Z is 32 over X, Y. Should I be worried about X or Y being 0?
Yeah.
Not really, yeah, because this is a box, and so. But whenever you have variables in denominators, you should think about that and think about whether it's reasonable or not to worry about zeros down there. Okay, so let's re-express S in terms of our two variables. XY plus, okay, 2y times Z is what, 64 over X? And 2x times Z, 64 over Y. So we now have something that we can optimize. Okay, as before, now we're separating ourselves from the physical problem, and we just have a math problem. So we start computing first partials. We get y minus 64 over x squared, and we get x minus 64 over y squared. And you can go ahead and do the mixed partials, or the second partials. Let me just, for the sake of time, get going on solving this thing. We want to find candidates. And that means setting these things equal to 0. Eliminate one of the variables, just start solving the system. I'm going to go the other way here. X equals 64 over y squared, like that. Take that guy and drop it into the first equation. And that turns into and you might factor that into y. Something like that. I'm doing a lot of quick algebra here just to get you guys out of here. So if you miss an algebraic step, you can catch me after class and I'll explain it. Two solutions to this, right? What are the two solutions? 0, which we don't care about, and 4. And we only care about 4. If y is 4, what's x? It's 4. Absolutely. Okay, if y is 4 and x is 4, what's z? Yep. And so we get 4, 4, 2, and what we see is a box with a square bottom and a fairly short height, whatever that means. Again, you might want to confirm that this is indeed a minimum. Go ahead and compute D, check those second partials, and confirm that this is a minimum. This can get very complicated. We're not going to go there in this class, but just know that this is the tip of a very large iceberg. And this is sort of the nuts and bolts, meat and potatoes, grind it out kind of max-min problem. You're going to see a much more elegant approach to some of these problems on Friday when we do the method of Lagrange multipliers. Really beautiful geometric approach to things. Until then, see ya.